Hello, this is my third video on rotational inertial calculation using integration. So this one's got to be the so far the most complicated one, and also happens to be 3D. So we know this from a past discussion. So let's draw this on the far right side just as a reference. So we have this, a sphere, a solid sphere, rotating around its symmetrical axis. Alright, and the rotational inertia is 2/5 mr squared. Okay, so we have that. We're going to prove it, but we're not going to do the whole sphere, and we're just going to do half of it, just the hemisphere, the top one, because if we know the rotational inertia of the top one, the bottom half also has the same exact rotational inertia, because it has the pretty much same mass distribution towards this rotational axis, although that distribution vertically is kind of upside down compared to the top. So if we only do the top half and then double the result, we'll be able to get the whole thing. All right, so that's our goal. So now let's draw a really nice hemisphere. So we'll start here with a dot. Okay. Here. So there we go. Okay, not too bad. Added some dashed lines, and we'll also add a vertical axis. We'll call it Z. Okay, so dashed line inside the body. All right, so that's the Z direction, and the hemisphere has a radius R. And we could say that the hemisphere has mass half m, but we don't really need that. We just say that the hemisphere has a density rho. Okay, so that's a volumetric density rho. And we're going to find the total rotational inertia of this hemisphere and then double it. All right, so this is our goal. Let's remember that. So let's recall what we did before. What we did before was, for example, a bar. We just cut a slice and we describe how much mass we cut out, how far is it to the axis rotation, and starting from there, we used the dm and also the distance r. We can integrate the rotational inertia, which is the r squared times dm, right? So then as we go to a two-dimension, we did a disk. So the disk is cut into concentric rings, and each ring we know the rotational inertia is going to be the delta m times r squared. And then r changes, that m also changes, and the mass is related to the area of the ring, right? So that's how we were able to get a small amount of rotational inertia from a ring, and then we integrated to find the total rotational inertia by integrating it. So we're going to use that expression. So we're going for the total rotational inertia is going to be the integral of a differential quantity's rotational inertia. You just add them all together. Except that now we have 3 dimensions, so we cannot cut rings anymore. We're going to cut disks. So how do we cut disks? We'll just cut these disks. So I just arbitrarily cut a disk. See how well I can draw with the these lines in the back. Okay, that'll do. So we just cut this disk. Here's the center of the disk, is located at a height of z. So this height is z. And it doesn't work too well. Let's put that z right here. And it also has its own radius, which is lowercase r. So we can imagine cutting or slicing this whole hemisphere into slices, like slicing an onion. So each slice has a different height, z, and each slice has a different radius, r. And each slice also has a different mass and also resulting rotational inertia. But as we slice this whole hemisphere into infinite amount of disks, and we can always put the disks back to return them into this hemisphere. So that's what integrals are for. First, you have to find the differential quantity, such as a slice, and then you can just sum up all the slices to make it back into this hemisphere. All right. So this slice, we were looking for a mass of the a small cut or a small ring. So now we're going to do the same thing, and we'll say that this slice has a mass delta m. And instead of proportional to linear density or area density, now we have volumetric density. So that density times delta V, the volume of this disk. Okay, so what is the volume of the disk? Okay, so let's try to work it out. This disk here, we don't have to cut it out and straighten it out into a strip, but this disk looks like a regular disk, although the edge is not really straight or vertical. We can imagine the edge is going to get closer and closer to be vertical if you slice the disk thinner and thinner. So this volume is going to be like this. So this volume just looks like a regular disk with straight down edge, so like a coin, just like that. So what's the volume of this thing? Well, the cross-sectional area and then the height, right? Here's this height. Because we have our z-axis running vertically, this height can be called delta z, a small amount of z change, and this area is pi r squared, right? So this volume delta v should be equal to cross-sectional area pi r squared, then times delta z. And once we go to a differential quantity by taking delta z's limit to approach 0, then we can get dv equals pi r squared dz. All right, so what else do we need to know? Well, we have the volume, so we can get a mass, right? So we can calculate this differential amount of rotational inertia contained by this disk. So for a disk, I know it's going to be a 1/2 mass. Now we only have a differential amount of mass, so dm times r squared, 1/2 mr squared, right? So how to get the dm? We have the delta m, right? So this delta m can turn into a dm with a limit equals rho dv, and this dv is equal to this quantity. So if we plug this in here, we get our dm. So dm is equal to rho, this dv is pi r squared dz. So now that we have dm, we can calculate how much rotational inertia that small slice has. So now that we have dm, we can figure out this di. So let's figure out di. So di is 1/2 dm times r squared. So 1/2 dm this whole thing, and then times r squared. I'll just change the power to r to the 4th power. Okay, so now we have di, but we have this r here. We need to turn this into a z. So let's move on to this side, we can draw this line to the base. So this distance is z. And then we can draw out r here. This is r. And from here to the center of the hemisphere is a capital R, 90 degrees. So we get r squared is equal to capital R squared minus z squared. And now we can substitute that into this r to the fourth power. So let's move to the left side. Now we know di, it is 1/2 rho pi. So the r to the fourth power turns into capital R squared minus z squared then dz. So now we can specify z. In order to have the slice built into a hemisphere, you have to start the slice from 0z and go all the way up to capital R here on the dome. Right, so this is from 0 to R. Alright, so now let's integrate. We need to expand this term. Right, so let's do 1/2 rho pi. So r squared squared, r to the fourth power, z squared squared, z to the fourth power. The cross term with a negative. Okay, so those are the terms. These are all simple polynomial terms. That is a constant of z, so it integrates into z, right? Z to the fourth power and second power, you can integrate those as well. So 1/2 rho pi, r to the fourth power integrates into a z, plus z to the fourth power integrates into z to the fifth power over 5, minus r to the second power integrates into z to the second power integrates into z to the third power. So 2r squared over 3 z to the third power. And we evaluate that between 0 and r. It should be easy. Plug in 0, you get 0. Plug in r, you get all of these into r to the fifth power. Okay. 1/2 rho pi. So that's r to the fifth power. Plus 1/5, also r to the fifth power. Minus 2/3, r to the second, third, r to the fifth power. You may be uncomfortable with r to the fifth power, but I assure you this row also has some r to some certain powers in the denominator, so you'll get to a lower power of r soon enough. Okay, so now we have r to the fifth power. We have a 1/5, and a negative 2/3. So we're gonna look for common denominators, and that would be a 15. Okay, so let's do this. So 1/15th. Okay, so 5 minus 10 is a 15 minus 10 is 5. 5 plus 3 is 8. So we have an 8 on the top. And 8 and 2, we have 4 on the top. So 4 over 15 rho pi r fifth. So that's the rotational inertia of the hemisphere. So for the whole thing, we multiply this by 2 to get this of the sphere. So it's 8 over 15 rho pi r fifth. And rho is density, so if the whole sphere has mass m and divide by the volume, so the volume of a sphere 4/3 pi r cubed. Okay, so plug that into the sphere's rotational inertia. Sphere 8 over 15. Rho is this m, and 4 pi r cubed and also a 3 flips to the top. And there's also a pi on the top, r to the 5th power. Okay, so divide that, so 15 turns into a 5, and divide this out, 8 turns into a 2, and pi is divided out, r to the 3rd power, r to the 3rd power, that goes into a 2, goes into a 2. So what we have left is 2/5 mr squared. 2/5 mr squared, which is what we were expecting anyway. So let's quickly review it. This time we were building up this hemisphere by slicing it into this more primitive shape, the disk, because we know how much a rotational inertia disk has. So we're able to write this, right? The rotational inertia of a disk is 1/2 mass times radius squared. And the mass is very small because the slice is very thin, and all of the rotational inertia of each disk will stack up into the total. So we're integrating to get the total rotational inertia, and then the dm, the mass, turns into a density times volume. So this density times cross-sectional area times the height, right? That's that. And then we have this r here, which is the radius of this slice. So we're using trigonometry to find out how it's related to the z and r in this relationship. So we plug everything in together. di is 1/2 mass times r squared, and then replace that r squared with this. So we continue on to the left side, plugged in what r squared is, and we found out this is just a few polynomials to be integrated with. So we integrated everything. We found this is for hemisphere, and we multiply by 2. This is for a sphere, and there's this quantity. Rho is the density, is the total mass over volume of the sphere. Mass is that, and that's the sphere's volume. And then do some cancellations, you get this value. Thank you.